Section 4.7, inverse trigonometric functions. This is kind of part 2. We've already done sine, cosine, and tangent inverses. We will now do cosecant, secant, and cotangent, and their inverses. So, as we kind of talked about before, when we did sine and cosine, we had to restrict the domain. So for cosecant, if we take a look at cosecant, it does not pass the horizontal line test, and there's many more of these U-shaped curves anyways, but they don't pass the way they are right now. And so once again, we are going to have to restrict the cosecant graph because it is not a one-to-one function. So where should we restrict it? Well, if you take a look, if we can take these U-shaped graphs and take kind of just part of them, so kind of starting right there at negative pi over 2 to pi over 2, and we only cover from here up and from here down, we cover all those range values. In this case, the range value is from negative infinity to negative 1, and from 1 to infinity, it covers all those values still, so we're good. So we're going to take and basically eliminate everything else just like we did the other day from this graph. So now that represents what we're going to use as our one-to-one function for cosecant. And so, what is its domain now that we've limited it? Now we have a domain from negative pi over 2. Now at 0, right here at x equals 0, it's undefined. So we'll have a break at 0, and then we'll go from 0 back to pi over 2 on this side here, where it's included. And so that's our restricted domain for cosecant. So now remember, with domain and range of our inverse, they just switch. So now the domain becomes the range. So that's from negative infinity to negative 1. And from 1 to infinity. So these are the numbers that can get plugged in as the input for the arc cosecant, or the inverse of cosecant, and the range is the domain of the original function. So that's negative pi over 2 to 0, or 0 to pi over 2. And you can see from the graph above, the y equals arc cosecant of x, that's the graph of the inverse of cosecant. And you can see in terms of 1 to pi over 2, and then negative 1 to negative pi over 2, and you can see that the 1 is going to infinity, and the negative 1 is going to negative infinity as well. So what do we really want to take from this? Well, just like before, we want to make sure that when we go to answer our questions, that we're answering in this range. So from negative pi over 2 to pi over 2, excluding the value of 0. All right, let's take a look at the arc cosecant of negative square root of 2. So we're trying to find the angle measure. So let's kind of look at our three main ones that are going to give us these values. So we have pi over 6, which will be square root of 3 over 2, comma 1/2. We have pi over 4. Those would be your square root of 2 over 2's. And then pi over 3, and that would be 1/2 square root of 3 over 2. So which one of those values is going to give us square root of 2 when we do the reciprocal? Well, it's going to represent the pi over 4 with the square root of 2 over 2. So when you take the reciprocal of square root of 2 over 2, you get the square root of 2. And that's something that you might remember with our exact values, since we've already done those. So now what do we need to do? Well, we need to make sure that we answer it where it is in the negative. So when you think about this on the unit circle, just to kind of give you another visual here, remember our restriction is from negative pi over 2 to pi over 2. So we have our positives here and our negatives here, and we'll be going from here to here, including these two, but not including 0. It's undefined. So since we're looking for a negative square root of 2, we want to make sure that we answer pi over 4, but we're not going to go around positive direction to get 7 pi over 4. We're going to have to go in the negative direction. And so when we do that, our answer would be negative pi over 4. Once again, what we're saying is that cosecant of negative pi over 4 is negative square roots of 2. And that has to do with the reciprocal of the y value. And the reciprocal of square root of 2 over 2 is just the square root of 2. And, you can take the reciprocal of 2 over square root of 2 and kind of do the math yourself. Multiply by the square root of 2 over square root of 2. You get 2 square roots of 2 over 2. The 2's cancel, and you're just left with radical 2. So that's why it works out. The negative, you want to make sure you go into quadrant 4, but you are going in the negative direction to make sure that you still fall within that range that we specifically talked about. So in this case, negative pi over 4 would be your answer. Alright, so let's move on to the next one, y equals secant of x. So once again, you have the same type of thing that you have with cosecant, but things were shifted over. So once again, this is not a one-to-one function, so we will have to restrict it. So on this one, kind of the same idea. We'll start at 0 and go to pi, and then we are able to eliminate everything that is not part of that. So we'll get rid of all of this. And remember, that graph kind of continues on forever as well. So all of it's is going to go away, and then this, we're going to go up until basically the y-axis. And so you can see now that this is a one-to-one function, and it'll go up to infinity, and then this one will go down to negative infinity. But it's still a one-to-one function, or it now is a one-to-one function, and so now we have restricted the domain. So the domain now will represent your values from starting at 0, including 0, up into, and then pi over 2, there's a vertical asymptote, so there's a restriction there, so we got to include that as not being part of our domain all the way to the value of pi. So secant is similar to the cosine's restriction, but we don't have that pi over 2 restriction that we have in secant is not in cosine. So that represents our domain. Our range stayed the same. When you restrict it, it doesn't change. You don't lose any value. So our range on this one will be negative infinity up to negative 1. And then from 1 to infinity. Okay? And then now when we go to look at arc secant of x, and you can kind of see the graph here in terms of its inverse, the domain becomes the range of its original function. So the domain will be negative infinity to negative 1. And these will be the values that get plugged into the function, or your input, and then from 1 to infinity. And then the range, which we really want to make sure that we're looking at here, is our solutions will only be values between 0 and pi, but not including the angle pi over 2. And so there's our range, and that once again is kind of our main focus with this, is that this is where the range for arc secant of x will fall. So let's take a look at example 2. Find the exact value of arc secant of 1. So let's think about this. Alright, once again, kind of getting your visual here in terms of your unit circle. We want to go from 0 to pi, but we're not including pi over 2. So we're going to go from 0 to pi, not including pi over 2. So once again, quadrant 1 is our positive, quadrant 2 will be our negatives, and they'll both be positive angles. So where is secant of 1? In terms of secant, you're looking for that reciprocal of 1. So once again, thinking about your ordered pairs. Now in our ordered pairs for square root of 3 over 2, 1/2 square root of 2 over 2, none of those have a reciprocal of 1. So it must be looking at one of our quadrantals. So this ordered pair would be 1, 0. This ordered pair over here is negative 1, 0. And so when you're looking at secant, which is the reciprocal of cosine, that represents at 0 radians, the x value is 1. So therefore the reciprocal of 1 is also 1. Therefore, arcsecant of 1 would be equal to 0. And sometimes when we start using values in the angles of 0, this represents 0 radians. So this is an angle measure, but it's in, once again, radians. So 0 radians. So arcsecant of 1 is equal to 0. Alright, and then our last trig function, we got y equals cotangent of x. You can see, similar to the tangent one, once again kind of shifted over, but we can just take one period, so we'll start at 0 and go all the way to pi, and then we will eliminate everything else. Once again, we're doing this so that we are making it a one-to-one function. So we'll get rid of all this stuff on the left side, and as it goes on forever as well. And then same thing on the right side. And then therefore, that creates a one-to-one function, which means we can find the inverse. So what's the domain? Now that we have restricted it, the domain for this is going to be all values. Let's make that a little bit smaller. All values between 0 and pi. And so that's definitely different than tangent because of the vertical asymptotes in terms of where they fall with tangent. The range is negative infinity to infinity. It's all real numbers. And once again, 0 and pi are not included because that's where the vertical asymptotes are. So when you go to look at the inverse of cotangent, or arc cotangent of x, there's the graph. Your domain is now all real numbers. You can plug in any number you want. And your range now becomes the domain of the original, which is all values between 0 and pi, not including 0 or pi, because once again, that's where those vertical asymptotes were. So we're going to take a look at some inverse cotangents and see if we can find the value. Let's take a look at example 3, arc cotangent of negative square root of 3 over 3. Alright, so when we look at this, once again, if you're aware of what value in terms of cotangent gives you negative square root of 3 over 3, that's going to help you out a lot. If you don't remember that, you'll kind of have to go through. Hopefully you know it's not a pi over 4 because that would be 1. So let's look at our pi over 6, which is square root of 3 over 2, comma 1/2. So if we do the cotangent, remember cotangent is equal to the, let me go back and do it this way. We'll do cotangent of theta is equal to x over y. So if I take the square root of 3 over 2 divided by 1/2, that 2's cancel and you're just left with the square root of 3. So for pi over 6, you get the square root of 3, which means pi over 3 must be the correct choice, but let's go ahead and show that. So that's 1/2 square root of 3 over 2. And once again, for cotangent, that's x over y, or in this case, 1/2 over square root of 3 over 2. The 2's cancel. And then once you rationalize it, you get square root of 3 over 3. So that's what we want. So we know it's a pi over 3. But which pi over 3? Well, remember with cotangent, we're going from 0 to pi. So we'll start at 0, go to pi. This represents the output. Now, we don't include 0 and we don't include pi. Those are restrictions. So what angle, in terms of answering this, arc cotangent of negative square root of 3 over 3, we've got to make sure, let's not forget about that negative. So this is positive, this is negative, and so we want to be in quadrant 2, and we want the angle in quadrant 2 for the reference angle of pi over 3, so that should be 2 pi over 3. And once again, what we're saying is if we take cotangent of 2 pi over 3, we should get negative square root of 3 over 3, which we do. So that finishes up the 3 reciprocals, sine, cosine, and tangent, which leaves us with secant, cosecant, and cotangent. And so once again, we need to make sure that we're aware of what these range values are, these outputs of all our inverse trig functions. So in summary, what can we write down for this? Well, I would pause the video, write down what you think is kind of the important takeaways from this, and when you unpause it, see if we kind of have the same thing. So this is what I wrote down for the summary. I wrote the intervals of the range for arc cosecant, arc secant, and arc cotangent, which are the ones we learned today. And then below that, I actually listed the first three that we learned: arc sine, arc cosine, and arc tangent. And you can kind of compare those to their reciprocals. But these are definitely the intervals of the ranges that you will need to absolutely know while you're going through and doing inverse trig functions.